Everyone, so hope you're all doing good. And with today's video, we will learn how to evaluate the performance of our code or solution that we present in an interview or in a professional setting. This is something that is very common for the software community to discuss about. So let's uh, let's just think about it in this way. Let's say you want to uh, send okay, we will come to actually this in a while. Just ignore that for now. Let's say you want to send a parcel from your home to not me, you want to send a file from your house to your friend's house. Now way there are multiple ways that you can send this file via, right? So one way is that you mail it to them. Right? The other one is that you book a delivery system and you put your file in a hard copy or in a pen drive and send it to them, or you ask them to come to your house, get the file, and then they can go. So these are multiple ways that you could have basically transferred this file to your friend. Now, if we discuss about how much time it would have taken, is like which one would have been the most efficient method to send this file would have been via email. Why? Because it would have taken the least time and the least effort by anybody else, right? So that is kind of analysis that we need to do for our code as well. Like these are the multiple ways to solve this solution, and among these, you realize that F4 is the most optimal function that you can use to transfer the data from you to your friend. Right? So this kind of gives you an idea of which method to use when. So there are benefits of each of these methods. I'm not saying that email is the only way. For example, let's say it's not a file, it's let's say a hardware that you need to send. In that case, email does not work. This function at all is not working. So only this and this functions are valid where you either send it via parcel service or you send ask them to come to you and then you give it to them directly and then they take it. Uh, so in that case, the parcel would be parceling it via some service would be the most optimal. But then what if it's highly confidential and something very fragile and you don't trust any of the parcel services? What do you do in that case? In that case, you have to ask them to come because you believe they will be responsible with the package and then give it to them and then they take it back. So based on the situation, based on the kind of solution you want, based on the inputs you get from your clarifying questions, based on the condition you are like the question that you get, change your solution. So how do you calculate how your code is actually performing or how your solution actually performs? So for that, we have something called a big O notation, and this notation is used to quantify two things. One is your time-based performance, and the other is your space-based performance, which means basically how much memory, extra memory you would take, and the time-based complexity will inform you how much approximately how will your solution change based on the number of inputs it gets. So that is where this graph comes in. So let's say you have a code that takes always, let's say, 13 microseconds to run. In that case, your solution is basically a constant time solution. So irrespective of whatever the input size, which is n here goes, this is something that you need to actually keep in mind when you're solving for interviews or when you're doing competitive programming. This is something that you will use very frequently. So based on the input size, the constant complexity big O notation solutions never change. The logarithmics change quite slowly based on the input size increase. Um, the constant time, sorry, the linear uh, complexity graph goes linearly based on this, like it grows linearly with the size of the input. So these could have represented time or space both. If I would have said time, that means it would take same amount of time irrespective of the size of the input. If it is logarithmic, it would have taken the time that it takes to complete the give you the result would be logarithmic in nature. As in, if you give it an input of size, let's say n, it will take log n time approximately to uh, give you the solution. Similarly, for n, this is how it increases linearly, like in a single one-on-one relation. If you give it n size input, it will take n amount of time. It does not mean it will exactly take n amount of time, but when we calculate this big O notation, there are some rules that we follow. One of them being that it is basically the closest function that will create an upper bound for the time and space performance of your function. So let's say if your function was something like this, the upper bound for this, like basically given, if you this is the kind of graph you get for multiple input sizes in an actual machine. Let's say you took this graph as t and then you have this graph as n, where this is input size, this is the time it takes. Based on your machine, it will take different amount of time for the same amount of input. In fact, it will take different amount of time the next time you give it a input of size in itself, because systems are not exactly going to take x amount of time. It completely depends on uh, the number of times you give it that input. Anyways, but in your case, what is the closest function that would create the tight upper bound for it? Could it be uh, n square? Maybe. Could it be n factorial? Maybe, because it technically is providing an upper bound. But is this the closest upper bound? Not really, because if you do this kind of linear graph through it, linear line, that might do a better job, right? But what if we give it a logarithmic chart, and we'll see that it will always go down only. So it needs to be down. This is the greatest value it can ever achieve. Like this needs to be the greatest value it will ever achieve based on the input size. So we would see that if you take a logarithm graph, order of log n, it kind of closely binds this function, random function that I drew, which was the actual times. So the time complexity of the solution that you give, you would report it as order of log n. How we calculate this, I'll come to that in a bit. But just to give you an example of what exactly this big O notation means, it is the closest upper bound for that function, that exact time function. Okay, now let's come to the rules when we present the big O notation. The first thing that you need to keep in mind is you drop all the values in that notation. So if you basically calculate, let's say, uh, big O notation of 2n, it is same as saying it's big O notation of n, time or space. The second thing is we completely ignore the lower lower terms. So for example, if you get a big O function of let's say n square plus n plus 1, that the 1, because we remove all the constants, and we'll remove n because the contribution of this n in the overall estimate of this time complexity would actually be negligible. Uh, a better example for this to actually show you how less it would be is, let's say, 2 to the power n. Also, do remember this graph, how fast 2 to the power n grows. I need another page. to the power n plus 1. So if you think about it, if we give n as, let's say, 10, this would become approximately 10 to the power 3 plus 10 plus 1. Now compared to this 1000, this 11 does not really make much difference to it, right? So you just ignore it. So instead of saying that this is the big O complexity, we will just say 2 to the power n, and this will give us the proper estimate as well. Because again, if you remember, we are just taking the closest upper bound estimate of it, of the function. Now that we have covered this part, you might be shouting at me, how do you calculate this function? We now understand that this is how you present it under an order of like the big O function. But how exactly do I calculate this part, right? So to do that, let's discuss the time and the space part little separately, because it's a little different in the sense that when we estimate the time, we are actually estimating the number of times a particular operation takes, right? So if say, let's say I have a function that just returns the table of 2 given a number a. You give it a number a and it will tell you what is the value of 2 times this number. So it will basically return 2 times of a. That's the whole job of this function. Now, if you look closely, how many lines of code does the CPU need to execute? Just this one, right? Uh, Executing this one line of code means it will take, always take a fixed amount of time. Let's say it takes 13 milliseconds. Now, does it matter uh, what A is? Like, it's basically is does the amount of time this function takes, do you think it is dependent on the size of the input? Not really. It will just double it and return. And the depending upon how big the value of A is, this value has an upper limit of like a fixed value. So we can safely say that, let's say, worst case scenario, your system is very slow. It will give it will give you an answer in 2 seconds. The worst case. I mean, it could give it much faster, but in the worstest case, it will give it to you in 2 seconds, right? So in big O notation, I would say this might be of order 2 second time complexity. But since we do not focus on the exact values and the constants, it will always give it under 2 seconds. So we can say that it is order of one. Right? This converts to one. Basically, any kind of constant value converts to one, which also is interpreted as constant. So in an interview, you can say it's order one, or you can just say it's a constant time complexity uh, solution. And similarly, if we take a little more another example, let's say I want to create a function of adding two numbers. For now, I'm just going to take the example of adding a and b, two integers. It's going to be an integer only, so we don't get into the complications of the languages. So let's say I want to add a and b. What I want to do here is uh, I want to take input of a, input of b, and then add it into a second variable and sorry, a third variable, and just return this some value of c. Now your function does two things. It takes the addition, it returns. Again, time complexity would be constant. But we want to also check, do we take any extra space? Extra space being, does the RAM need to create a one more memory allocation? It does, of C. So it will always take one integer's worth of extra space. Integer worth space. Now, if I give it, let's say, two very large numbers, do you think this extra space that we need changes at all? It does not. We just need to give it one integer's worth of space all the time because that's where it wants to create the sum and store it. So we can say that it will take constant amount of space as well. Now, you could be like, why do we actually need, why do we even need this extra space? Why can't we just, sorry, let's function add. I take A, I take B, and then I say B is equals to A plus B. Why can't we just do that? We just saved allocating extra space. Technically, you can do that, but before doing this, you should be very careful that generally it is not a good idea to modify the inputs given because there is a possibility this is not passed by value, it could be passed by reference, and you might be changing main data and making it corrupt. So before being doing going forward with changing the input, exact input that has been given, you should always clarify with your the input data, input variable, its input at itself. In which case you can do some cost cutting on the space that your solution uses, and you can save some space basically. But the question here is also, do you actually need to for a constant space memory solution? The answer is yes. If you can reduce space, do it. If you can reduce time, do it. If modifying the input can reduce your complexity, even if it is constant, even if there is a micro, okay, so if there is a micro improvement that is there, don't bother wasting too much time in the interviews specifically. But if there is a micro improvement, generally I would prefer to add those improvements as well to the solution at work. So yeah, make sure that you give the most optimal space and time complexity uh, optimized solution. uh, so let's take a little bigger example and understand how do you calculate a little complex functions, time and space complexity. It's just a little because I want to move you from constants to a little more function, complexities where the rate of change would be a function. Uh, so yeah, basic. Oh, also if I forgot this function that you put in the order O of n notation, this is actually the rate of change in time or space as the input increases based on the input in relation to input. So let's take a look at few examples of how you would calculate. We'll start with time complexity and then we'll get to space complexity as well. So let's say I want to put print a table of two where I take the input of how many like how long I want the table to be. It will start from one, and I want the user to be able to define what the n would be, where n is the last number with which the multiplication result they want to see. So I take n as an input, integer input from the user, and how would we go ahead with creating this table? We would directly just create a for loop, and we will say initialize it with I is equals to 0. I actually will have to start it with not 0 but 1, unless again, now this decision should not be solely taken at your own uh, discretion. You have to ask the interviewer, do they want the table to begin from 0 or from 1? Irrespective of how trivial this question might look, there might be a condition where the interviewer or the program that you're actually going to submit would have required you to also consider zero. So it's better to clarify these things. Even in job, you have to clarify these kind of questions and not just assume. You have to be very vocal about this kind of questions. So for our case, it will start with 1. So for int I is equals to 1, I plus I is, we want it to go till, sorry, we want the loop to go till I is less than and equal to n, and we increment I by 1. Now all we have to do in this for loop is just print uh, 2 times I, and we would be done with it. So if we count the number of times this instruction is run, uh, we can very clearly see it will run one time for I is equals to 1, one time for I is equals to 2, one time for I is equals to 3, and so on and so forth. So in all totality, for I, if I goes from 1 to n, this will actually run for order of n. So we can see that it will run for each value of I from 1 to n. So it will run for a total of n times. And since this is a constant time operation, it will, let's say, take c time to execute this. We will say that it will take total of c times n time, right? And since in our O notation we get rid of this, eventually the time complexity would be order of n only. We'll just ignore the c. Sorry, not to 0, it actually goes to 1. Right now, how much space are we using to create this? And I mean extra space, not the space that the RAM will need to take to load this function on, initialize this for loop, create this instruction set and execute these. I'm talking about the extra space that it took. As of now, we are not taking any extra space. So I'd say it will take constant time because we always assume that these operations will take constant time only for the RAM to load all these things, instruction set and all. And this part also is not taking any space, so it takes overall of constant space. Now, even if I would have had another variable uh, called product is equals to 2 into I, and then printed product here, it still takes only one integer's worth of space extra. So I would have still been gone with it. It takes a constant space. So for this simple program, the time and space complexity would be time is order of n, space is order of 1. This is the most optimal you can get in any solution. Now let's think, can we reduce order of n somehow? So this is the kind of algorithmic thinking that you need to have. For this question, it's very evident, but you have you when we will see some complex problems, we would have to constantly ask ourselves, can we go even more optimal? So here we'll see that can we somehow reduce the time from n, order n. So you can see that we have to always go for all the n. Anyways, we'll have to run this n times. So we can't go any lower than order of n. And here the time complexity would increase linearly with the number n given by the user, and hence the time complexity order of n. Now let's go for a more interesting problem, interesting time complexity, like a code that has a little more interesting time complexity. So let's say we have this function called, hmm, what, let's just call this a function. And what it does is it takes an input n, and the question is, you are given a bacteria that doubles in population every day, and we want to find how many days it will take for the population to be n, right? So this kind of problem, what we want to do is we want to count the days, which will start with 0. Why it starts with 0 is because, let's say this n itself is 0, the first day we are done, right? Then what we want to do is we want to check while. So what our plan is, it doubles every other day, which means we'll go from n and keep halving and count up till what value can we get before n becomes 0 or 1. So while n is greater than 0, which is even if it is 1, we'll consider this. While n is greater than 0, actually, let's think about this selectively. If the bacteria initially itself is 0, do you think that it can double at all? If the value is 0, it will never be able to increase anyways, right? So we have to check the first day, basically, it needs to be at least 1. Right? So since count days is initialized with 0, if we did a n is greater than 1, and if we return just 0, that actually would be correct, right? So I don't want to run this loop if n is smaller than or equals to 1, which is while n is greater than 1. Another way to say is while n is greater than 1, I want to run this loop only then. What I want to do with it, I want to half it and increase the count of days because it doubles every day, so it will half every previous day. So what we do here is n is equals to integer division by 2, and then I say count days plus plus. This will increase the number of days, and will actually we are just counting back basically, right? And eventually after this loop is done, we will just return count days and we are done. Now, what do you think will be the time complexity of this function? So to calculate this, what we want to know is how does the time varies as we increase n. So if n is equals to 0 or 1, the loop runs only once, like the whole code runs only once, loop runs 0 time. Let's say if n is equals to 2, what happens? First time you enter, n becomes 1, the count becomes 1, it runs once. N goes from, actually the loop runs 0 times, right? So I'll just say loop is equals to 0 times. This time loop ran 1 time. Uh, then if n is equals to 4, let's say, I'm going to just take even numbers, actually powers of 2, just so that we get an idea of how this is progressing. If n is equals to 4, the first day it will become, like when count is equals to 1, the n goes to 2. When count becomes 2, n goes to 1, and the loop closes, which is it runs 2 times. Similarly, if n is equals to 8, we can see very easily that it will run 3 times. So basically, how is the loops, how is the number of times the loop runs changing based on what the value of n is, we can say loop runs, number of times, how many times loop runs we have to calculate. Let's say the loop ran k times to complete the total of going from 1 to n. We can very easily see that n is equals to 2 to the power k in that case, right? Now we want to know how many times the loop ran, which is how many times, what is the value of k basically. What we will do is we'll simply take log on both sides. This is base 2. If we take log base 2 to the power k, by the property of log, this k comes to the front. And okay, so this becomes log base 2n is equals to k log 2 to the base 2. This value again by the property of log becomes 1, which implies k is equals to log n base 2. Now if let's say we, instead of doubling it, tripled, we would have gone with n into the division 3, in which case the whole series would have been 3 to the power k, where so the log also would have been to the base 3. So just to avoid that confusion, we just ignore the 2 here, and we say that the time complexity basically would then become order of k, which is not even, it's equals to order of log of n approximately, actually would be better to say. So we will say that actually Bego notation you don't approximate, it is actually log n. So we'll say that the time complexity of this program is order of log of n. Now let's go ahead and see if we took any extra space. This function being loaded, the loops being loaded, the basic initialization of this count. So we take one extra integer space of like 32 bits basically will be used in the memory space. And do we take any other extra space? We don't really do that. So space complexity remains to be order of 1. Now let's take another, I'll ignore the whole function creation. Let's just take a snippet of code, because thinking about what could less than n I plus plus, thinking of a situation where this could be done, I'm not able to really come up with an example on the spot. So let's just for now keep it this way. J is equals to 1 while j is less than I, j plus plus. So what here, this just does something like some instructions. We'll just assume these are constant set of instructions. Like it takes constant time to execute these set of instructions. Now, what do you think would be the time complexity of this function, like of this for loops? So to calculate this, again, the best instruction, like best advice I can give you is, if you're not sure what the time complexity is, just count the number of times this part, the static part, constant part will run, and you'll be done. So let's take multiple values of n and the number of times the inner loop runs, and we'll just add that up, right? So if n is equals to 1, the inner loop will run once. 0. It runs once. So let's make it 0 just so that we can go with the less than sign only. If n is equals to 2, inner loop runs for 2 times. The value is 3, it runs for 3 times, so on and so forth. So if the value is n, sorry, not if, actually the value, when the value of I, I'm sorry, this is not n, actually this is I. When the value of I is n, it would have run n times. And the value of this, if you focus just on this part runs for I n times basically. This whole part runs for n times, and each time the number of times the constant part runs is different. So we can just add all these n values, and if we do that, we see that it is just nothing but sum of all the natural numbers till n, for which you might have studied the formula exists. The sum of n numbers is n times n plus 1 by 2, which means the time complexity would be this function n of n plus 1 by 2. If we expand this, it will become order of n square by 2 plus n by 2. And since this is the smaller value, again, based on the rules, we ignore this. So overall, time complexity would be order of n square by 2. This 2 becomes 1 because this is what we do with the constants, we make it 1, and this says that our time complexity for this would be order of n square. We can see the function of n square. This is how your n to the power k somewhere between here would be n square, the parabolic function. It's actually parabolic, it's not. I don't know why it looks like that. Let me just make it more parabolic chart of order of n to the power k. Somewhere around here would be order of n square also. I've created a general graph of order of n to the power k because you can just imagine if k is equals to 2, it goes through somewhere here. 3 will start to increase from here, and just as in k increases, it starts to go faster upwards. That's the only difference there. So you can see this is how your time would change based on what input size you have given for n. So this was how you calculate these functions and how you calculate time complexities. We will be calculating it for every problem that we go forward with. So eventually it will become like a second nature to you. So you don't have to worry if it's getting too complex as of now. I would say, however, go ahead, type uh, problems to practice for time complexity, space complexity calculation. You'll find some really good uh, practice problems. Uh, this is a very important skill for any interview because every time you provide a solution, your interview will ask you for square solution to sort like 10,000 products for 1 hour. Even 2 minutes is too much these days. So yeah, we will eventually dive into all those things, how to optimize, how to think about those. But yeah, do go ahead and practice a lot of problems on calculating time and space complexity. Some companies like Amazon actually directly also ask time and space complexity given one set of instructions. So if you are applying for SDE1 level roles, they you expect direct questions for time and space complexity from at least Amazon. Other companies, I'm not sure, but they might also, anyways, they'll have to ask you to calculate the time and space complexity for your solution. So I will put the link to some of the resources where you can go and practice these problems. And if you have any questions, any doubts, put them in comment, message me if you need. Uh, and I will see you in the next one. So bye bye. Take care till then.